This is geometry lesson 14.7, lengths of chords, secants, and tangents. So the big idea says when two lines intersect each other and also each intersect a circle, so you can see that here on the right, we have two lines that are intersecting each other and both lines also intersect a circle. The lengths of the segments from the point of intersection to the circle are related in a surprising way. So we're talking about the length from the point of intersection of the two lines to the circle. So the distance from P to A and the distance from P to B is going to be in a special relationship with the distance from P to C and the distance from P to D. Okay, now right up front, the one trick to this is to not think that these are proportional. Okay, we're not cutting up this and this and this and this and setting up a proportion. It's going to set up in a little bit different way. So here's the theorem. Suppose one secant intersects circle O at A and B. So we've got that right here. And a second secant intersects circle O at C and D. If they intersect at P, which they do here in this picture, then PA times PB, so notice not PA times AB. That's what everybody wants to do, this times this piece. It's the distance from P to A, and then the distance from P to B, which would be the whole length here. Those multiplied together equals PC times PD. So I'm going to go ahead and drop some numbers in here so you can see what this is. So if I put this as a 6 and I put this as a 4, I'm going to go ahead and put this as a 5. Now, everybody wants to do 6 times 4, so be careful. When we set up this relationship, if I set it up here, PA times PB, that's going to equal PC times PD. So PA times PB, that would be 6 times 10, not 6 times 4. 6 times 10, the full length here, the full length is 10. So it's 6 times 10, which is going to be 60, is going to equal whatever PC is, which is 5, times PD. Now everybody wants to call this number that. They'll call this X, they'll solve, and then they'll say CD is that number. We got to be careful. It's the whole thing is X. So we can get fancy here with our algebra, but in this case, we can solve this pretty simply. Just make sure that we know that X is the entire thing. So if this is X, I know 6 times 10 is equal to 5 times the whole thing. So this is 5x. I would divide by 5 on both sides, and x equals 12. But this out here is equal to 12. We got to be careful. Everybody wants to put 12 in here. So the full length PD is 12. And so if I wanted to find out what CD was, I would have to take the 5 from the 12. So to get this piece right here, I'm going to do 12 minus 5. Okay, the whole thing's 12. This piece is 5, so 12 minus 5 equals 7. So that piece right there is 7. So again, 6 times 10 is equal to 5 times 12. Now, we're also going to see, so if I reset this up, it was 6 times 10, and it's equal to 5 times 12. So both of those relationships, when I multiply, give me 60. Okay, and that number right there, what both of those pieces multiply to, is called the power of point P. So whatever those segments are going to multiply to, that's called your power of P. So let's say for a second that you wanted to call this piece X when you were solving it. The other way you could do this, and I don't necessarily recommend this way, but a couple of you might like it. Again, if we have PA times PB, PC times PD, so starting over. If I did the 6 times the 4, 6 times 10, see I made the simple mistake there. 6 times 10 across, and then PC is 5, and I want to call this X. If I wanted to do that, then I wouldn't do 5 times X. This whole side is what PD is, so it would be X plus 5 if I wanted to solve directly. So what this setup will do will get us this number 7 directly. Where if you think about this setup, it got us the 12, which was the full length, and then we had to go one extra step to figure out that this was 7. So if I call this piece x, that means the whole thing is x plus 5. That's where this 12 will eventually come from, 7 plus 5. But if we didn't know the 7 yet, it's x plus 5. I would solve this out. So 60 equals 5x plus 25. When I distribute, you would minus 25 from both sides. I'm going to get 35 equals 5x, and I would divide, and x equals 7, which again will get me that piece. So you could set it up like this. You got to be careful. If you call this x, don't go 5 times x. That would be 5 times the whole thing, which is x plus 5. Otherwise, do it like we did originally. That's what I would recommend. It's 5 times the whole thing. The whole thing's x. We found out that it was 12, and then once you know the whole thing is 12, you can subtract them to figure out it's 7. Okay, so just like anything, the first time you see it, it probably feels difficult because it's new, but this actually makes a lot of sense and won't be that difficult for you, I don't think. So example number 1, circle at the right, we have chords A, B, and C, D. They're intersecting at point P. So this is an example of this when P is on the inside of the circle. Still going to follow the same rule. The distance from P to one point of the circle is going to be equal times P to the other point on the circle is what we're going to be looking at here. So remember, it was the distance from P to A times the distance from P to B. So here it's going to be the distance from P to D times the distance of P to C. I might have just kind of confused you saying that all out loud. So let's go ahead and set this up. So from point P, I know I can go to D, and I can multiply that same line times the distance from P to C. That's going to equal the distance from P to A times the distance from P to B. So when it's on the inside, it's actually easier because I'm not going to have that overlap where I had P to A was 6 and P to B was 10, and there's an overlap there with the two different distances. Not going to happen here. It's just going to be the 4 times the 3 for this line, and it's going to be the 2 times, we'll call this x, and I don't have to get fancy. It's not the whole segment. So when this point is on the inside, we're not doing 4 times 7, the whole thing. We're just doing 4 times 3. The distance from that point of intersection to the side of the circle times that point of intersection to the other side of the circle. So it's just 4 times 3. It's 2 times x. So that's 12 equals 2x. You divide by 2, of course, and x equals 6. 4 times 3 is 12. 6 times 2 is 12. Okay, so the power of P is whatever they both multiply to, and that is 12. So the power of P is 12. And we solve for x here. That is equal to PB. So PB equals 6. So it looks a little bit different when the point's on the inside. It's actually easier. And so we'll do a couple more of those examples on the back. But now let's see what happens when we have a tangent. What happens here? So the tangent length theorem says let P be any point on the exterior of the circle. PT is a tangent. Remember, that means it only hits the circle once. Then the power of P for the circle is PT squared. So up here we had that line. It was a secant. It hit in 2 spots. So it was this distance times this distance. Well, we're going to think about like this hits it twice, but at the same spot. So it's that distance times that distance. So the power is just going to be PT squared. So how does that set up? So if I had this situation right underneath of it without some of the extra lines drawn, and I had a tangent PT and I had a secant PB, we know down here it's going to be PA times PB, that distance. Okay, I've got that point of intersection on the outside of the circle. The distance to A times the distance to B up here is going to be PT. And since it doesn't have another point of intersection, it's times itself. All right, and that's why the power here is PT squared, because on this side, that's what's going to happen. PT times PT is PT squared. So if I knew what that distance was, let's say it was 6, it would be 6 squared is 36, and that would be your power of P, and that came again from 6 squared. So when you have a tangent, it's just going to be times itself because there's not two different pieces to use. Okay, it's pretty straightforward, pretty easy. So let's try one of those here on the back. So example number 3, we've got one line that's a tangent. Okay, we're going to be looking for that length here. We're going to find GE, so we'll call that X. And then the other line that's coming from that point of intersection G is a secant. It hits it twice. And so we know that relationship is going to be the length from G to H, which is 3, and then the length from that same point G to F, which is 9. The whole thing is 9. So when this sets up, the tangent is going to be times itself, GE times GE. And then the bottom part is going to be GH times the whole thing, GF. And after we do this a couple times, I think all of a sudden you're gonna get it. And you're like, oh, okay, I see the relationship. So GE, we're just gonna call X. We don't have it, so it's gonna be X times itself, which is just X squared. GH is 3. GF, be careful, is not 6. It's 9. Everybody wants to do 3 times 6. That'll be a silly mistake that people make. This length times that length, the distance from G to H, the distance from G to F. Okay, so that's 27. So some number times itself is 27. We're square rooting that. Depending on what the question asks, it might just ask for a decimal version here. If we're going to give an exact answer, we are going to need to simplify this. So I can split this into square root of 9, square root of 3, right? Because 9 times 3 is 27. That's actually what we did up here. Square root of 9 then is 3, and the radical 3 stays. We've done a lot of these this year, but just a reminder, you can always double check yourself. Square root of 27 equals this. So if I do 3 radical 3, what I believe the simplified version is, I should get the same answer. If I don't, then I know I didn't simplify correctly. So I know I'm good right here. And then using that same number, I'm going to go ahead and give the decimal version 5.9196 approximately. All right, and that was GE. 3 radical 3, approximately 5.196. And then again, the power of P here is what the two sides are multiplying to. 9 times 3 is 27. This one times itself is going to give you 27. This squared is 27. So the power of P, or in this case G, I should say, is the 3 times the 9. It's 27. It's what both sides multiply to. So this one squared is 27. A little more complicated. Use the easy side. 9 times 3 is 27. All right, 2 more examples to hopefully if we missed some of this the first time, we can get it this time. So we have a point on the inside. We're going to solve for PB, which we'll call X, and then also the power of P. So let's set this up with letters first. PD times PC, always the distance from that point to the outside of the circle. Okay, so that's going to set up 5 times 4, which will be 20. Has to equal the distance from the point to the outside, PA, times the distance from that point to the other side, PB. So that's going to be 2 times X. Okay, so 20 equals 2X. We would divide by 2. X equals 10, which is equal to what we were looking for there, PB. Oops, should include all of it. 10, PB equals 10. And again, the 5 times 4 is 20. This 10 times 2 is 20. Power of P is 20. It's what those two segments are multiplying to. All right, and then number 3 looks very similar to the one up there, some different numbers though. GE is a tangent and GF is a secant in its 2 pieces. Reminder, we need the distance from G to F, not this distance of 8 in here, so you're going to put those together. So the distance from the point to one of these points of intersections is 4, and the distance from the point to the other intersection is 12. Don't use the 8. And then up here, we're looking for GE. We'll call that X. Since it only hits the circle once, we're going to times it by itself. So it's going to be GE times GE on one side, and then it's going to be GH times GF on the other side. So this is X times X, which is X squared. Over here, we're going to have 4 times 12. So that's 48. So something times itself is 48. We're going to square root, not a perfect number. Now, we know 49 has a perfect square root, so this is going to be real close to 7, but it's not going to be exact. So x equals, the best way to split this one up, you could use 4, but 16 is going to be better. 16 times 3 gives me 48, so I'm going to do 16 and 3. Square root of 16 is 4, so it's 4 radical 3. Again, I can always double check myself. Square root of 48 is not a perfect number. It's almost 7 because square root of 49 is 7. But then to double check my simplifying, I'm going to do 4 radical 3, and I'm going to get the same answer. So I know that my simplified version is good. If they wanted me to give a decimal and round it to whatever, it's 6.928 or whatever they asked for, 6.9, 6.92, just depending on the question. Okay, so that is equal to GE. That's what we were looking for. And then the power here is whatever those two sides would multiply to. It's 4 times 12, or it's this number times itself. Use the 4 times 12. That was the 48. So the power of G equals 48.